Hi, my name is Rudolph. Within the next few minutes I'll give you some insights about how AVL FIRE M can help you developing internal combustion engines and their components. FIRE M is a 3D CFD simulation software developed by AVL. Our internal combustion engine simulation capabilities help developing well-functioning and robust solutions for gas exchange, fuel provision, combustion and emission, exhaust gas aftertreatment and engine thermal load to meet customer expectations and legal standards. Let's look at all these points a little bit more in detail. First, let's look at intake and exhaust systems. The intake, but also the exhaust system, plays an important role when it comes to engine performance. Their design impacts gas dynamics and respectively the amount of charge provided to the individual cylinders. If an engine is operated with returned exhaust gas, the intake manifold design additionally needs to ensure proper mixing of the exhaust gas and the fresh air. To help developing manifolds, FIRE M offers multiple options. Depending on which is selected, results are provided faster or more accurate. This correlates to the needs during the different stages of the development process. While, for example, quick analysis of multiple designs is needed during the concept phase, accuracy is more important than speed in the detail design phase. With the release of Cruise M and FIRE M version 2026 R1, also a 1D to 3D co-simulation option for intake and exhaust manifolds is offered. It ensures always correct boundary conditions for the 3D simulation and minimizes the calibration effort needed for the 1D model. Intake and exhaust ports are typically not seen as part of the intake or exhaust system, but nevertheless, their design is of decisive importance when it comes to engine performance and efficiency. This is why developing and optimizing them is a standard task in the engine development process. And simulation is widely used to achieve the targeted performance indicators, which are discharge rate and swirl or tumble number. To perform these simulations, FIRE M users utilize the so-called port workflow, which enables them to set up model generation, execution and analysis of a complete series of cases, each representing a different valve lift, within minutes. And above all, the modeling approach underlying the FIRE M workflow accurately reflects the environment and procedure used in hardware-based tests on a flow test bench. Therefore, simulation results and measured data are directly comparable. Most of today's internal combustion engines are turbocharged. Using FIRE M, our clients investigate how the flow in the compressor develops at different operating points. This helps them to ensure the component's performance and to avoid stall. Also, FIRE M offers all that is needed to efficiently and accurately analyze the thermal load of the compressor. Let's now look at in-cylinder flow modeling. Simulating combustion. More precisely, gas exchange, fuel provision, air-fuel mixture, ignition, combustion and emissions, is the DNA of FIRE M. The software spray, wall film and combustion modeling capabilities are well acknowledged by leading automotive companies and their suppliers. They enable our clients to determine reliably the impact of design and operating parameter variations on performance, efficiency and emissions. The basis for this excellence was formed in intensive research activities with partners in academia and industry. Combustion development is a very demanding task. It requires addressing and understanding many aspects and phenomena, as listed on this slide. Therefore, at AVL, we have not only integrated the most suitable simulation models into FIRE M, but also engineering and testing experience which AVL has accumulated over decades of developing internal combustion engines. This is a unique approach, and it is seen by us as the best way to support our customers in developing internal combustion engines, regardless of type, size or used fuel. For example, engines running on fossil resource-based fuels, such as diesel or gasoline, hydrogen, dual-fuel applications like diesel ammonia, as shown here. With FIRE M you have chosen the right tool to develop them all. Most modern combustion engines feature fuel injection systems. Simulating all related phenomena is a challenge for many CFD codes. But not so for FIRE M. FIRE M users can benefit from in-depth modeling of all physics related to fuel injection, such as fuel primary and secondary breakup, droplet turbulent dispersion, distortion and drag, collision and coalescence, wall interaction, wall film formation, as well as heat transfer between gas and liquid phases and solid walls. This level of detail is of utmost importance in the development of predictive simulation models. A particularly valuable feature of FIRE M in this context is the so-called nozzle interface modeling capability. It connects the nozzle interior flow simulation and the simulation of the fuel spray in the cylinder by passing the flow conditions in the nozzle orifice's outlet sections when releasing the fuel into the combustion chamber. This enables a precise prediction of the primary fuel breakup, which is a precondition for accurately modeling all subsequent fuel injection-related phenomenon. But not only this. FIRE M offers the possibility to model cavitation and erosion through cavitation in the spray holes of injection nozzles. In combination with the nozzle interface capability, FIRE M thus can predict how the performance of a fuel injection nozzle changes over lifetime. The nozzle internal flow simulation also predicts fluid velocity, density, vapor, and liquid volume fraction depending on the given boundary conditions, which are primarily the pressure in the fuel supply line, the pressure in the combustion chamber, and nozzle geometry. If the latter has changed over the injector's lifetime due to cavitation inside the nozzle orifices and erosion accordingly, the conditions in the orifice's outlet sections change. The resulting difference in the flow pattern cause different fuel sprays in the combustion chamber. For the displayed instance in time, the new injector provides a narrower spray angle and a larger penetration compared to the aged, eroded injector with its wider cone and shorter propagation. The nozzle file interface is also deployed when investigating nozzle tip wetting. Wetting of fuel injection nozzle tips can lead to significant raw emission formation, such as soot and unburned hydrocarbons. The example shows, in black, a relatively small soot cloud in front of the almost dry nozzle tip, shown in this slide in the center left. While the cloud in front of the wet tip, in the center right, is significantly larger. The conclusion from this analysis would be, ideally, any nozzle tip wetting should be avoided. If that cannot be accomplished, design your combustion chamber to enable evaporation of deposited fuel before the flame arrives at the tip. The same FIRE M capability is also used to analyze AdBlue nozzle tip wetting. Wetting of AdBlue nozzle tips favors deposit formation and can, in the worst case, lead to malfunction of the SCR aftertreatment component. For both, fuel and AdBlue injection nozzles is true that the amount of tip wetting can be influenced by nozzle design, nozzle protrusion, and air motion in the vicinity of the tip. Not only injection nozzles, but also the fuel supply through carburetors is simulated using FIRE M. Makers of small engines, such as for chainsaws or mowers, carry out such simulations to determine and optimize air-fuel mixing in all operating modes. The movement of the valve in the supply line is controlled by the pressures on top and beneath the valve. The displacement is calculated online during the simulation, which makes use of the Eulerian multiphase capabilities of FIRE M. The Eulerian multiphase module was also utilized in the simulation, which was carried out to investigate the crankcase ventilation of a hydrogen-powered ICE. The yellow surface represents the oil in the crankcase. The oil is moving due to interaction with the ventilation air, the air motion due to cranktrain movement, and because of the interaction with the cranktrain itself. The ultimate target of this simulation is to figure out whether and if, how much hydrogen is entering the crankcase and where it accumulates. The info about whether and how much is provided by a FIRE M in-cylinder flow simulation that is linked to an Excite piston and rings model. Excite provides the amount of blow-by and FIRE M provides the hydrogen concentration in it. With such simulation we are able to determine the regions with high hydrogen concentration. In the figure on the right, they are indicated in red. In this particular case, the derived flammability index is very low, although this tells us that there is no danger. A large number of our software clients use our simulation solutions to support the development of exhaust gas aftertreatment components, like catalysts, filters and dosers and complete systems. Doing so, they typically start their work by performing simulation in 0D or 1D using AVL FIRE M. This is because FIRE M models run much faster than FIRE M models, even in real time, and hence enable investigating many cases in very, very short time. Contrary to FIRE M, FIRE M is used to perform analysis tasks that require exact consideration of geometrical details and their effects. For example, determining and optimizing flow or ammonia uniformity in front of a catalyst. These simulations requires running a 3D CFD simulation in FIRE M. FIRE M is also strong in modeling the AdBlue injection in front of SCR catalysts. Simultaneous to the AdBlue injection, FIRE M computes AdBlue and wall interaction and the potential formation of wall film, which may result in the formation of urea crystals, like biuret, triuret, cyanuric acid, amylide, amylene, and melamine. If this is the case, FIRE M will predict this too. Species conversion is simulated in FIRE M, if the impact of the inflow conditions on catalyst heat-up and conversion efficiency shall be analyzed. FIRE Classic also offers simulating loading and regeneration of diesel and gasoline particulate filters. This capability helps, for example, developing filter regeneration strategies. Filter regeneration simulations are often connected to the thermal load analyses of filter bricks. These simulations can help preventing cracks in the filter structure caused by thermal stress. I think you've already realized how powerful our exhaust aftertreatment simulation solution is. Still, I'd like to give you a few more information. Exhaust gas aftertreatment simulations are also performed on system level. System simulations are typically performed in 0D or 1D. Means, FIRE M is the right tool for it. Also, for predicting vehicle test and drive cycle emissions, FIRE M is the tool of choice. Important is, the physical and chemical models applied in FIRE M for 1D simulations and in FIRE M for 3D simulations, are consistent. This is a unique feature of the AVL aftertreatment simulation solution. It allows to perfectly balance modeling speed and level of detail throughout the whole development process of an exhaust gas aftertreatment component or system. Use just the tool that fits best to available inputs and analysis targets. The results are consistent across dimensions in space. The last use case of FIRE M which I like to highlight is engine thermal load analysis. FIRE M's reputation is to a significant extent also built upon its heat transfer modeling capabilities. These are essential to determine the thermal load of combustion engines and their components. Exemplary, we are looking now at the so-called head block compound. Boundary conditions for this analysis tasks, including coolant mass flow and temperature, are derived from FIRE M simulations. This is essential especially when simulating transient engine operation or thermoshock tests. Further boundary conditions are obtained from FIRE M combustion simulations, which provide load-dependent heat transfer between in-cylinder gas and structure, and a FIRE M coolant water jacket simulation which delivers the heat transfer between coolant and structure. The results of the FIRE M simulations allow the calculation of the thermal load on the cylinder head block assembly. The solution is applicable to simulate both steady-state and transient engine operation. Remains for me to add that the just described thermal analysis methodology is applicable to a variety of powertrain components, such as piston, turbocharger, exhaust manifold, and others. If you engage in the development of combustion engines or their components, FIRE M is the right tool for you. Our solution supports you decisively in developing zero-impact emission and CO2-neutral ICE-based powertrains with fast and predictive virtual analysis and optimization of gas exchange, combustion, raw and tailpipe emission and thermal load to meet key performance targets. This is possible due to scalable physical models for balancing speed and performance. All features are accessible through a modern GUI, a powerful scripting environment and dedicated, validated and automated workflows. And all of this is based on the innovative power of a team that has always been committed to clean mobility and for almost 4 decades to virtualization. And finally, not to forget to mention, we are always with you. Not only virtually. A worldwide network of real AVL simulation experts is available to support you in doing your day-to-day business effectively, efficiently, timely, and close to you. With this, I'd like to thank you for your time and your attention. I'd be happy to meet you again for an in-depth discussions on topics you are interested in.